Welcome back, everyone. We're going to continue with the program with Viktor Abramov. He's going to talk about Biunits in ternary algebras of hypermatrices. Viktor, the floor is yours.
Yes, thank you for introduction, and thank you for invitation to give these online talks. In this talk, I will consider structures which are very similar to the ones which were considered by Richard in his talk. And so the first structure which I'm interested in is a ternary algebra of hypermatrices. So by hypermatrix, so you understand, I mean an nth order hypermatrix. So it's a complex valued variable with three subscripts. It's denoted T and subscripts I, J, K. So where I, J, K, they integers and they run from 1 to n. So for this kind of objects, we have several names, and so we have no firmly established terminology in this field. So the same are called cubic matrices, three-dimensional matrices, spatial matrices, and even three-index matrices. So I will use the term hypermatrices. Hypermatrices, and so I will consider the hypermatrices of the order 3. So, and of course, this hypermatrices is very interesting objects because they so to speak, provide a natural building material for ternary products. So I will assume that hypermatrix is defined on a Euclidean space. And so in this case, I have no difference between covariant and contravariant indices. And so I will use only covariant, I mean subscripts. So, and in this case, when I change a coordinate system in Euclidean space, so I will consider this hypermatrix as a SO3 tensor. So it will transform under the action of the rotation group. So the Euclidean space will be three-dimensional. So all subscripts runs from 1 to 3, and this I will call the third order hypermatrix, or simply hypermatrix. But I will also assume that it's a tensor. So when I have a change of coordinates, it transforms according to the by the rotation group, and this is shown on the next slide. So of course, here we have an addition and multiplication by complex numbers. So we have a structure of the vector space, and this vector space is 27-dimensional. And now the action of the rotation group on this vector space of hypermatrices is defined by this. So here these two are hypermatrices, and the G is an orthogonal matrix with determinant equal to 1. So I will use, but this of course natural, Richard used this Einstein convention that repeated indices, we mean summation over the repeated indices here. So we have a summation over I, J, and K. So, so yeah, we can, so I can say that this formula defines an action of rotation group on the space of hypermatrices, or the hypermatrices. Or I can look at it from the point of view of representational theory. Then I can say that I have a tensor representation of the rotation group. So if I take an element of the rotation group, put it here, then I have a linear transformation in this 27-dimensional vector space of hypermatrices. And so from this point of view, from representation theory, so what we know about this representation, tensor representation? So actually we know that the whole space can be decomposed into the direct sum of 4 subspaces. They're written here, and the subscript here means the weight of representation. So we have, this is, it's very important that this decomposition is unique. So we can uniquely decompose into the direct sum of these subspaces, and in each subspace, we have a representation of the rotation group, which is multiple of irreducible one. So, in each subspace, we have a several times repeated irreducible representation. And the general method to get this irreducible representation, we have to split each subspace into direct sum of subspaces, of course, in a way which is invariant under the action of rotation group. And then in each subspace, we will have an irreducible representation. For example, the first subspace is a zero-weight subspace. Here we have only one-dimensional representation, and this subspace is of totally antisymmetric or skew-symmetric tensors, which is written here because this epsilon, of course, this is not epsilon, this is the same as Richard used in his talk. This is a Levi-Civita symbol. So totally antisymmetric tensor. And this is one-dimensional space, and we have one irreducible representation. Next one weight representation. This is a space of third order, well, of course, hypermatrices or third order tensors of this type. And here we have 3 times repeated irreducible representation. And of course, we can split this subspace, this subspace into 3 ones according to this, like this. And then we have an irreducible representation. So I'm most interested in the weight 2 representation space, this one. Why? Because first, in this subspace, we have twofold irreducible representation of rotation group. So this space is 10-dimensional, it's written here, complex dimension. Complex dimension is 10. So if we split it into the direct sum of 2 subspaces, then there will be 5-dimensional subspaces, and in each subspace, we will have an irreducible representation of the rotation group. So this space will be most interesting for me. And the third one is a subspace of totally symmetric tensors. This is a 7-dimensional, and here we have only one irreducible representation, so no need to split it into subspaces. It's an irreducible representation of the rotation group. So now about this space. So what we see here, we see that, how can I say by words describe this space? This is traceless hypermatrices. So traceless means that the trace over any pair of subscripts is equal to 0. So the first one here, I take a trace over first 2 indices, subscripts, 0, first and the third one, and here second and third. So about this, I will say that this is a traceless hypermatrix. So the trace is over any pair of indices is 0. And now here you see that we have one more condition, and here we have a cyclic permutations of subscripts, and the sum of the values under the cyclic permutations should be 0. What is the motivation? Okay. So and now I will study this subspace of hypermatrices. And
can I ask a question?
Yeah, please.
Can you go back to the previous slide for a moment? So why? I guess that you can also have a SO3 cross SO3 cross SO3 action, right? On tensors. You could have it, right?
Oh, yes, you mean SO3 times SO3 times SO3.
Yes.
Yes, I can say this, yes.
Okay. So, but now we are just looking at sort of the diagonal action of that, right?
So I transform each subscript
With the
I,
same.
j, k with these matrices.
Yes. So it's always the same matrix. It's some kind of cubic diagonal action.
Yes. G is the same. Yeah, G is the same.
Okay. Yes. Just clarifying. Yes. Thanks.
And related to that, so reason why you wanted to consider that, because you said that you used some kind of motivation from what? Yeah, because I was missing a bit of the motivation on the back, of the interest specifically in that. But I guess it's already interesting itself to consider that.
Yeah. But motivation will be later.
Yeah. Okay.
Usually I start with the motivation, but now I decided to start not from motivation, but first from the algebraic structure, and then to explain what kind of motivation will be here. So here we have a tensor representation for the rotation group. Now uniquely can be split into these subspaces. And now here I will have a twice repeated irreducible representation of SO3. And if I want to distinguish with irreducible representations, then I have to split this subspace in turn into two 5-dimensional subspaces. How can I do this? This is not unique. So here we have several possibilities. But I think the most natural one that we solve this equation, and here we use a primitive third-order root of unity. So now, Richard denoted this third-order root of unity by J. I denoted it by Q here. So you should keep in mind that in Richard talk, this was denoted by J, but I don't know, I used to denote it by Q. So here we have properties of this parameter. So the sum 0, and if I take a complex conjugate, then I get this q squared. So, and this is a general fact that any hypermatrix can be represented, can be decomposed into the sum of 3 components. Actually, Richard used in his talk this decomposition. So I can write here sum of cyclic permutations without q. Here's the sum of cyclic permutations multiplied by conjugate q conjugate q, and vice versa by q and q conjugate. So now if I took the sum of these components, these 3 give me t I j k, this and this 0, this and this 0. So I get t I j k. So it's some kind of identity. So, but now if I restrict this decomposition into this subspace, then due to this condition, the cyclic sum is equal to 0. I get that the first component is 0. And so now if I restrict this decomposition, so by other words, I assume that this hypermatrix belongs to this subspace. Then I have only 2 components, this one and this one. So, and they are denoted here prime and 2 primes. So, but if I study the properties of these components, then the first components, I mean the property under the cyclic permutation of subscripts. So if I perform a cyclic permutation of subscripts for this component, then it's easy to find that it transforms like this. By other words, if I perform a cyclic permutation, then the right-hand side will be multiplied by q conjugate. In the case of the second component, if I perform this cyclic permutation, then it will be multiplied by Q. So Richard showed the same kind of variables in his talk, but in this context. In this context, why I use this decomposition? Because I wish to decompose this space into two 5-dimensional subspaces. And this formula shows that I can do this by taking these components or projecting this hypermatrix first to this subspace and then to this subspace. So actually this formula shows that I have a decomposition into two subspaces. And these subspaces can be defined as follows here. They're written here. So, but this is important here that I also have this traceless condition. So first, I have hypermatrices which transform under the cyclic permutations with the Q bar or Q. But I have an additional conditions that the trace over any pair of indices is equal to 0. So so we have no firmly established terminology in this field, and Richard called this J skew-symmetric term. Then I call this q-cyclic hypermatrix. So q-cyclic hypermatrix means, in my talk, means that first it transforms under the cyclic permutation with the Q, and of course, this hypermatrix should be traceless by any pair of indices. So now the direct sum of these two subspaces gives me this subspace. And in each subspace, in this one and in this one, I have an irreducible representation of SO3. Now motivation is here. The motivation for this is a Ternary generalization of the Pauli exclusion principle, which was proposed by Richard. So his reasoning comes from the model of quarks. So we know that quarks are most fundamental particles of matter currently known, and all hadrons are composite particles made of quarks. And Richard mentioned in his talk that fermionic baryon is a combination of 3 quarks, and the meson with integer spin is a pair quark-antiquark. So, and we have 3 generations of quarks, and in each generation we have 3 flavors, which are denoted, up, down, charm, strange, top, bottom. And of course, all combination of quarks should be colorless. And in quantum chromodynamics, quarks are treated as fermions with half-integer spin. And in this sense, they obey the classical Pauli exclusion principle. But according to quantum chromodynamics, in a stable bound state, there is place for 2 quarks in the same U state. For example, proton is a UUD or D state, 2 D states. Neutron is a combination UDD. So, and the Richard proposed generalization, which he called Ternary generalization of Pauli exclusion principle. No 3 quarks with identically equal quantum characteristics can form a stable configuration that is perceived as a strongly interacting particle. Of course, I'm not a physicist. I'm a mathematician, and I know that physicists sometimes say that there are some excited states of which live a very short time particles which admit the 3 equal flavors. But if we assume that this is stable, configuration. Then this Ternary generalization of the Pauli exclusion principle will be okay. So, but algebraically, what does it mean that no three quarks can be in the same identical quantum state? So, for example, if we have a wave function of a quantum system of three particles, and we denote the quantum states of this particle like this, and the value of the wave function on these states we denote by this. So it's very, we can see here an analogy with the hypermatrix. So then, according to this Ternary generalization of Pauli exclusion principle, when these subscripts are equal, then the wave function should vanish. And now, if we take a superposition of this of three states, then for this superposition we will have the same. So if we put here this superposition state, the value of the wave function should be 0. But now, if we take into account that this wave function is linear, then we find that the wave function should satisfy this condition, where we have all possible permutations of subscripts. And now we have several cases how we can solve this condition. First one, when we assume that this wave function is totally antisymmetric, and this will be consistent with the Pauli exclusion principle of Fermi-Dirac statistics. So, and from algebraic point of view, the algebraic structure which is adequate to describe this situation is a Grassmann algebra. And now, for me, it's very important that here we see that the wave function will be traceless. So if we take the trace over any pair of indices, it will be 0. Of course, it seems a bit strange because, of course, it's natural when we assume a total q-symmetry. Of course, it's natural that, and people usually do not pay attention to this. But for me, it's important that the trace over any pair of indices is equal to 0. So now we can solve this condition in another way. We can assume that the sum of cyclic permutations, this part of the left-hand side of this equality equals 0. Then, of course, this will be also 0. So, and now you can see where the motivation comes from. So here, now I will show the representation theory. So here we have a hypermatrix which satisfies this condition. In this condition. And now, of course, we can solve this equation by assuming that the wave function has this property or this property. And you can see that by this, from representation theory, by this, we split this space into two subspaces where we have an irreducible representation of SO3. But I would like to draw your attention that that in my construction, I always assume this additional condition that the trace over any pair of indices is equal to 0. At the first glance, it seems technically. No, of course. First reason why I require that the trace is 0 over any pair of indices is representation theory, because in this case I can put it into the frame of representation theory and to get an irreducible representation of SO3. But when I think about this, it seems to me more and more natural, because if I do not assume that the trace over any pair of they are traceless, then I go very far from this, I would say, classical case, Fermi-Dirac statistics or Pauli exclusion principle, or from Grassmann algebra. But if I require with that the hypermatrix should be traceless. Then I would say, then I can put all these cases on the same roof. So they're not very far from. So they maybe, of course, it's not a rigorous explanation, but they are more closer to each other. I do not go very far from this classical case. So now about this hypermatrix. So this is technical. So I put the entries of this hypermatrix like this. So here I have by blue color, I have an entries with the first index subscript 1. Then the second black with a first subscript 2, and the third red one with the first subscript 3. And the other indices, second and third, they the same as enumeration of entries in the square matrix. 1, 1, 1, 2, 1, 3. So now it's it is to see that in hypermatrix, if I put it into the space, I have 3 directions, and I call them.
Can we briefly interrupt and ask? So the link here would mean the transformation, the relation between the T1 matrix, right? Hypermatrix. Sorry. How you can.
What kind of relation?
No, okay.
So this is more closer to us. This is in the middle, and this is far from us. I I put these entries, replace these entries in the 3-dimensional space like this. Okay, it's not very important because it's maybe important for me because I imagine this hypermatrix. Its entries in the space like this. So now I have a structure here. So I have 3 directions. So because I usually denote these entries, I will go back a bit. But I will denote it I, J, and K. I is the first, J is the second, and K is the third subscript. So I call this direction is I direction, because here I have an increase of the first subscript, 1, 2, 3. Then this direction I call J direction, because here I have an increase of a second subscript, 1, 2, 3, and the third one is this one. This is the K direction, because now then the third subscript increases by 1 here and 3. So and actually I can cut this cube by planes which are perpendicular to the corresponding directions. If I cut by planes perpendicular to the ith direction, I have these square matrices. When I cut by planes perpendicular to the j direction, then I have these matrices and so on, and so on. These matrices, they are square matrices 3 by 3, and they are very useful in what follows. So here I show these directions, how I split this cubic matrix into square matrices. So how I will denote them? I will denote them like this. For example, if I fix the first subscript, well, then I will show here by this superscript. So this shows that the first subscript is fixed, and the value of this fixed subscript is 1. So I get this matrix. Here I fix the first subscript, but the value of the first subscript is 2. Then I get this black And the red one is this. I fix first and give it value 3. So now I split it into the matrices, and I will use these matrices later. So now, but I can also represent all information, all entries of this hypermatrix by taking these square matrices and writing them from the left to the right. So the blue one will be this. Then this black one and this. So here I have all entries of this hypermatrix. So now in this talk I will be interested in algebraic structure based on a ternary multiplication. And so you know that an algebraic structure called a semi-heap, which is a set equipped with a ternary multiplication, which is denoted by dot, and which satisfies the generalized associativity. If I have 5 elements, then this ternary product satisfies this generalized associativity. So this is also called, I used to call it a second order associativity, but I see that that in paper I will show it. In the paper written by Carlos and his collaborators, heaps of fish, they called this generalized associativity. So I decided to call it in this talk also generalized associativity. So when H is a vector space, then the whole structure is called a ternary algebra. So this is a very good because by ternary algebra, different authors means different structures, various structures. And I like this terminology. So vector space and ternary multiplication, generalized associativity, which is a ternary algebra. I think this is a very good terminology. So I mentioned this paper. It's the date of this paper is written here. So there you can find an excellent overview of the theory of semi-heaps. I would say that I knew not very much about semi-heap and heap theory, and for me it was very interesting that Soviet mathematician Wagner developed this semi-heap and heap theory, and his motivation came from differential geometry, where we have a smooth manifold and atlas of a smooth manifold, which consists of local maps and transition functions. For me, it was very interesting. And now I will also use the same terminology proposed in this paper. So the neutral element for ternary multiplication. So we have a biunit, right or left. For right biunit, we have this condition. So here, right biunit is denoted by E. A is an arbitrary element of a semi-heap. If we multiply it from the right and get the same, we call this a right biunity, or it's called a right biunity. And for left biunity, we have this condition. So, and if E is a right as well as left, it's called a biunit. And the heap is a structure where any element is a biunit. So we have this for any A and B. And of course, it's understandable that in the case of the transition functions, we have this. So now I will remind you a theorem. We proposed this theorem in the paper, which is date of this paper is written here. It appeared in 2009. So in this paper we have several things, but one of them is the associative triple products. So we prove the theorem that if ABC and so the complex hypermatrices, then we have only 4 different triple products which obey the generalized associativity. It's interesting that generalized associativity, and these products are written here. So, and if here we have a diagrams which shows how we take a summation over the subscripts. So here first and in the first, last in the first, last in the second, and in diagram we simply connect them by corresponding lines. And so if we look at this, then we see that these two are very similar to these two, and some kind of similarity. I agree that we have some kind of similarity here, but these two products, triple products, are different. So, and I remember that my doctoral student, Sergei Shvitov, I posed him a question. He was from computer science, but he was interested in mathematics, and I posed him a question that can we find all triple products of hypermatrices which obey either associativity of the first kind. This is simple associativity. You have 5 elements and you group them by brackets. First on the left, then you shift brackets to the middle, and then you shift the brackets to the right, and all this should be equal. And it turned out that there are no such ternary products which could obey this first kind of associativity. But we found 4 products which obey the second kind of the associativity, which is called here in this talk generalized associativity. And I would say honestly, I forgot about this result. But when I saw this paper, Heaps of Fish, it reminded me of this, and I decided my idea was to apply this, to study these products in the case of the q-cyclic traceless hypermatrices. Why? I will explain on the next slide. Okay, it's for me it was really interesting. First of all, when I read the paper Heaps of Fish, I couldn't understand what is a fish product, but fish product. But then I understood that if you depict this diagram, so these triangles, and you put this marked by red, where you take summations, and it actually resembles the silhouette of a fish. So, but I will consider not a fish product. Fish product is the last one. I will consider the previous one here in this talk. I will consider this ternary product. And to distinguish between them, I will denote, maybe it's not very important. So I will consider this product. This is a fish product, but I will consider this one. So why? Because I was interested in SO3 invariants of hypermatrices. So as you see, I have a tensor representation. So I will say that I have a connection of an SO3, as Carlos says, SO3 times SO3 times SO3. And it's very interesting what kind of invariance I have here. So what kind of invariance of a hypermatrix? So first one is a linear. Here we have a complete table of linear and square and quadratic invariance. Linear invariant is only one, this one. But in the case of the q-cyclic traceless hypermatrix, it doesn't give anything, it vanishes, because this equals 0 and this equals 0. So now the table of quadratic invariants. So here you can see that this is complete table of quadratic invariants, and starting from 8, I have only zeros, because in each product I have a trace. For example, here I have JJ, 0, KK. No, okay, it's from this starting from 0. Only these 5 could be non-trivial. I'm sorry, 7, maybe non-trivial invariants. And now, if I look at this invariance, then I see here, for example, this invariant. I take JK, and this is very similar to this product. So here I have this part of the ternary product. So I calculated this invariance of the case of the q-cyclic traceless hypermatrices, and I found that there are only 2 non-trivial invariants, this one and this one. All other either zeros or they can be expressed from these 2. And if we look at this invariant, then it's not very hard to see that actually this defines a Hermitian metric on the space of hypermatrices. Why? Because look here, we take ijk, we multiply each entry of the hypermatrix with the same entry. So we interpret them, let's say, as a complex vector in the space, and here we have a complex conjugate. So actually, this is a Hermitian product, and it's not very surprised that we can define now the Hermitian product, Hermitian metric on this space, and we define it like this. Of course, this is invariant under the action of the rotation group. And the second invariant is this one. And my idea was that this invariant can be obtained from this ternary product, from this one. Now, I calculated both. So first of all, now we have a Hermitian metric on the whole space of third order hypermatrices. But I'm interested not on the whole space, but only on the space of q-cyclic traceless hypermatrices, which is 5-dimensional. And so this Hermitian matrix gives me a possibility to find an orthonormal basis. And I found it. This orthonormal basis consists of 5 hypermatrices. This. I will say one more time that I consider the space of q-cyclic traceless hypermatrices. So trace over any pair of indices is 0, and they satisfy this transformation rule that cyclic permutation multiplies by q. So this is a 3 and 2 more hypermatrices, this one. So, and this basis is orthonormal. So if I calculate the Hermitian product of these matrices, this is Kronecker delta. And now I can identify any point of 5-dimensional complex vector space with a hypermatrix. So now I have an identification, or by other words, I parameterize 5-dimensional space of q-cyclic hypermatrices by these 5 parameters. I call them coordinates. So now I have an identification, and for me it's very interesting because motivation comes from Ternary generalization of Pauli exclusion principle, which potentially holds in a quark model. And now I have a very interesting geometric space, 5-dimensional complex space. Each point of this is a hypermatrix, some kind of cube, some kind of have a cube structure. So, and I think maybe this is an adequate geometry for the quark model. So now, what about this ternary product? So I decided to find this ternary product, this one, not this product, but this one. in the case of a q-cyclic traceless hypermatrices. And when I started calculations, I found that these kind of matrices have a nice property, so which is written here. So if I cut, as I explained before, if I cut them by planes perpendicular to one of the directions, then I have three square third of the matrices. For example, I take case direction, then which means that I fix the third subscript and put it value p. Then the corresponding here, I have three matrices here. They are written here. So, and they satisfy the very nice relations. So if I take a product with the same subscripts here, then the trace of this product is this bilinear form. I will explain what this form is, because this form is, for me, is very important. And if these subscripts are different, then I multiply like this: u, v, vu, I interchange the order, I interchange them. Then it turns out that this is a traceless matrix. If I calculate the trace of this matrix, it's 0. Why it's important, I will show later. Now, what is a k here? K here. Now, if I calculate the invariants, two independent invariants, the first one gives me a Hermitian metric. This is a canonical Hermitian metric calculated now in coordinates of this 5-dimensional space. But the second one is this bilinear form, and here is the matrix of this bilinear form. And I was very interested for this invariant. Geometric meaning is very understandable. This is Hermitian metric, but what this kind of invariant gives, so I can interpret this in different sense. I can look at this as a tensor. As a tensor is a 5-dimensional complex vector space where I have a unitary transformations, because I have a Hermitian metric and I can reduce the whole group of non-degenerate transformations to unitary transformations. It transforms like this, and I studied the property of this invariant, and we wrote a paper, published a paper. So here in this paper we studied the geometric meaning of this invariant. First of all, it's symmetric, it's unitary, and these properties are invariant under the unitary transformations. Determinant is epsilon. By epsilon, I denoted here the 6 for the root of unity. And of course, it also has some additional properties, but these not unitary invariant, they are real unitary invariant. So if we take the 6th power of this matrix, it's an unit matrix, and eigenvalues also invariant here. And so we studied the geometry of a complex dimensional Hermitian manifold with additional structure determined by this invariant. So on each tangent space of this manifold, we have this invariant. And for example, an example of such a manifold is as U6 factorized by U5, but it's not directly related to the material of this talk. Maybe I will continue now. So here I multiplied and I get this bilinear form. And now it's useful to introduce the notion that hypermatrix.
Yes, Richard has a question. Let me bring the microphone closer to him.
No, are the 6 matrices which are traceless? Can you express them as Gell-Mann matrices, 3 by 3?
Richard, you mean these matrices?
Yeah. You have 6 traceless matrices, yeah?
Mm-hmm.
Gell-Mann matrices are also 6 traceless matrices. No, 8, sorry.
8, because dimension of SO3 is 8.
Oh, yeah, 8. So maybe it's a subset.
It's an interesting question.
This is probably without Cartan subalgebra.
Maybe, yeah.
Yeah, I think, yeah.
Yeah.
There are the 6 ones which are not commutative.
So I have to think about this. It's very interesting.
Okay, thank you.
Maybe here will be a relation with SO3. Maybe.
Yeah, must be.
Maybe.
Must be. Yeah. Thank you. Sorry.
Now, so I call the hypermatrix I to regular if the second invariant is non-zero. So it can be calculated like this, or if I wish to calculate it, so I have an identification. Each hypermatrix is parameterized by these 5 coordinates. I can calculate it in coordinates. In coordinates, of course, it's in coordinates. It's this. Oh, it's the same, it's equivalent. So if this second I to invariant is non-zero, then I call it regular. Why? Because now I look at the ternary triple product, which is different from the fifth product. So now I'm interested in this part of this product. Now I see that I can write it, I can put it into this way. Here I fix P, this is a third subscript. Here I fix K, this is also a third. So I have 2 square matrices, and before and earlier I denoted it like this. Then you can see that I multiply as these matrices and take the trace R. So now the triple product can be written if I introduce an auxiliary third square matrix H. It's introduced like this. So I multiply these sections, square matrices, and then take a trace. And now the whole triple products can be written here at the right-hand side. So I have this H auxiliary matrix. But now I remind you that these matrices have a nice property, which I showed before. Oh, I'm sorry. I missed this. Yeah, here, this property. So when this subscripts equal, I have this bilinear form. But when they're different, then and I interchange them, then I have a traceless matrix. So which gives me the following result. If now I interchange this here, U and V, so I will have minus here, because this is a trace. And the trace of the sum is 0, so which means that if I interchange U and V, then I have minus here. And this shows me that this triple product is antisymmetric, skew-symmetric with respect to U and V. But what does it mean? It means that if I put equal U and V, then the non-diagonal part will disappear, it will vanish because of skew-symmetry. But when they are equal, I will remain only with the diagonal part, which is this bilinear form. But what does it mean? It means that if they are equal, and then here I will have a delta, and which means that I simply multiply this T by this bilinear form, which is very similar to neutral element, to the right biunit. So, and now it's really so now I calculated all this. So the diagonal entries of H equal to this invariant, but non-diagonal part. Of course, I said that from this property, it follows that it should be skew-symmetric. We can see it here that it's skew-symmetric with respect to U and V. Here we have these coordinates. And also it's skew-symmetric with respect to P and K. And so here in order to put this general formula, I introduced this some kind of analog of Levi-Civita symbol, but this is some kind of Q analog of this Levi-Civita symbol. I needed simply to write this formula because I have three different matrices, and to put it by single formula, I have to use some kind of this Q analog of Levi-Civita symbol. So now, for me, it was very interesting that this is. So when I looked at this, I didn't see immediately that actually this is a bivector. So I have two 5-dimensional vectors, and the second order determinants composed of their coordinates. This kind of object is called bivector, and bivectors is closely related to Clifford algebras. But today I'm not able to explain why bivectors appear here. So now we can prove a theorem. So if U is a third order traceless, q-cyclic, and I to regular hypermatrix, then this hypermatrix will be a right biunit of the ternary algebra of third order hypermatrices, which means that if I multiply, this is not fish product, multiply from the right, then it will be the same. So for me, it was very interesting that in this ternary algebra of hypermatrices, we have a family of right biunits, and even they form the whole subspace of q-cyclic traceless hypermatrices. So that's all. I don't know how about the time.
We are around at the hour mark, but we have 5 minutes and some questions as people would like to continue.
I missed the notation actually that you used where you introduced. Can you please go to the I2 regular matrices?
This one.
Yes, thank you. Okay.
So I have a question actually on this slide. You say that this product is or is not the fish product?
This is not a fish product.
And this is the second, because it has a twist in the indices, right?
Yes, this is the second one. So I twist here these indices, not the same order. I twist them.
Yes, I see. So, okay, maybe let's get to the end, and then I'll ask my question at the end, because I want to, because that theorem seems very somehow expected in a sense in this context, because of the shape of the fish product up to symmetry of the matrices involved. So that might be the. So maybe I missed it because I had to take a call briefly. But did you relate this product to some concatenation of binary products and a transpose?
Yes.
Okay.
Yes, and the fish product in this construction, the fish product is closely related to the Hermitian metric.
Yeah.
Because in the fish product we have the same order. When we multiply, so we have.
Yes.
Here we have the same order, RS and RS.
Yes.
And this is very similar to this invariant. Which is a Hermitian metric. And so I think that the fish product will generate the Hermitian metric on this subspace.
Okay. Yeah. But what I mean is you can express, if you take the hypermatrices, you take as matrices with a multi-index. So you look at the first two indices as a multi-index and the third index as a single index. So you can regard them as ordinary matrices, but just grouping the indices. Then the expression of the product looks like, in the fish case, it looks like A times B transpose times C, or
Yes.
but the other one obviously is twisted from that, so it doesn't look like that. But under some symmetry conditions of the matrix involved, we will have some behavior like.
Yes. If I assume this q-cyclic behavior of this matrices under the cyclic permutation, then of course I can transform this from one. Yeah.
I see. So that's how I understand that theorem. It's correct to think that it's essentially that I am doing U hat transpose times U hat, and U is essentially unitary in that sense. When you go to your theorem in the further slides, right? There in the formula. So this idea of a biunit, especially a right biunit.
Right biunit, yeah.
Yes, right biunit. If this weren't, so if I just take the fish product, not this one, but the fish product,
yes,
then a right biunit is equivalent to once you express with multi-indices to a unitary matrix, basically some kind of unitary property where you have U times U transpose equal identity, right? So I guess this is weaker than that, but it's a similar sort of situation, I imagine.
You mean some transposition here?
Yes, I mean that exactly. So, well, it would be in the middle one, but yeah, same idea, because the fish product will literally be a transposition of if you group multi-indices in 2 and 1 and 2 and 1 and 2 and 1. In this case, there's a twist, so it won't be the case explicitly and literally, but up to some symmetry of the matrices involved, it might be the case. And so I wonder if this theorem, this result, can be interpreted as these are the conditions that you require to define a transpose for a particular subclass of matrices, which they're a bit more general than unitary because they need not be square, for example. Right. So, but they do satisfy this condition of unitarity, that matrix times transpose equal identity, right? So maybe that's a way to rephrase this result. I'm just wondering.
Yeah, and also
maybe yes, yeah.
Okay, yeah. Just
Yeah, and I also had the related question to this slide related to Victor, to the fact that if you basically then you have this property, like the one which you wrote, the one on the TU, yes. But I wonder if there are other, the TUU equal T, yes. But I also wonder whether that there can be also other, because you have been also referring, I think, to other possible geometrical kind of representation, not only fish product, whether when you have some other invariances, right, not the first one which you had, but other ones in the slide where you had many right properties, the invariances. Can you go to the invariances slide? This one. Yes. If some other, I don't know if you looked at them, but basically it's needs to be combinatorically somehow probably looked at, whether they will lead to some other properties, not the TUU equals T, but something else. If people looked at it. Do you know what I mean? Because basically you kind of described this theorem, some general, property of these ternary objects, but I wonder whether there are other properties of these ternary algebras that you could describe with that in this general form of the last theorem. If you go back to the slide with this theorem, because you were this one.
So I think that there may be the interesting properties of this ternary product. So maybe this was the first step when I studied the question of by units. But I think there are more interesting properties in this ternary algebra which I have to study, and maybe I think I mean that my idea was that the ternary product, these ternary products, they are very fundamental, and the geometry, some geometric objects are like a metric, like invariants, can be generated by these ternary products of the hypermatrices. And maybe even this by unit can also be interpreted in the framework of geometry, but I don't know how this can be.
Yeah.
Thank you.
Something in that direction. I don't know if you had seen I had a paper on bi-unit pairs. So when you, instead of having a single, it's a very simple. Did you see it, Richard? So there's it's a very simple idea that you replace, instead of two elements being the same, you replace, and you have some u prime or ab or something, and then you look at the pairs as acting as a unit. So that equation, but having u and u prime for some other prime, and so I can send you the paper, because it's I did some work with an algebraist in Edinburgh a couple of years ago, and we found some really nice little theorems about these pairs. So essentially, we found them for semi-heaps. So these are closed algebras. So it's not exactly the same as these products, because obviously these products need some conformality conditions. But for square or cubic hypermatrices, like you might have here, there are some interesting results about, for example, if you have a bi-unit pair, so AB satisfy the equation ABX equals X for all X, it turns out that BA is also a bi-unit pair. So, and it turns out that if you have if there exists a B for a given A, for which AB is a bi-unit pair, then B is unique. So there's all these nice results about bi-unit pairs that generalize the notion of bi-unit element, which is just plugged twice, right? And so maybe that's another interesting way to sort of generalize this sort of environment. I find it super interesting, by the way, the fact that you're finding some of these invariants for this product is something that we thought about but never really did. And a direct way to generalize is to think of bi-units. And so if I can give you my interpretation of the kind of thing that these bi-unit objects are, they seem to be, I mean, we thought of a generalization of so a semi-heap can be thought of as a heap can be thought of as a group without a choice of an identity, right? So of a neutral element. So it's essentially a group, and you can choose any element, and that element becomes your identity, right? So in the case of semi-heaps, we wanted to generalize, and so for semi-heaps we defined bi-unit pairs. So now you have two elements in the set. It could be the same by coincidence, so to speak, but they're generically two different elements. And then you said, well, what is the class of objects that have all elements be part of a bi-unit pair, in the same way that you would say that a heap is a semi-heap where all elements are a bi-unit in the usual sense. And so we know that there's a correspondence between groups and pointed heaps. So the idea was, what is the analog of pointed semi-heaps with bi-units, right? And we call these things di-heaps, as in double heaps or something. And we just don't know what they correspond to. It's an open question whether there's a family of. We know it's not groups because of these examples. Exactly, your work is showing there are examples of non-empty semi-heaps that have bi-unit elements that are not just reducible to simply groups of matrices, right? So we know that there are more than just groups, but also we know that it contains all the group cases because of when you take the bi-unit pairs be just two elements at the same time. So anyway, I'll send you the link if you want, because it's a very simple, very short paper. It's just some observations almost. It's not a very deep paper, but it has some interesting observations on biunit pairs. Okay. Was there? I don't know if this was a natural conclusion point, or you wanted to mention something else. Otherwise, we can maybe have some round of questions if someone else wants to ask. Richard, do you have a question to follow up?
I already asked. Can you say again what a die is?
Yes. So a die heap. So a semi-heap is an algebra like the ones that have been shown here. That has
With
this.
the Biunits.
Maybe Victor had the axiom somewhere. Oh, there's the
Yes, semi-heap is a set equal to the ternary multiplication, dots, which satisfies the generalized associativity of this kind. But look, when you shift these brackets to the middle, then these two second and fourth should be interchanged.
Yeah, so the middle one is U and, is that right? U and B are swapped, right? So the left side is ABC UV, the right side is ABC UV, but in the middle you have a UCBV, right? So U and B are swapped.
Okay.
So you can get that behavior exactly if you define, given a group, for example, or given matrices, just usual matrices, you can define a product that is A times B transpose times C, or A times B inverse times C. That ternary product will satisfy that equation exactly. So, an algebra that just satisfies that is called a semi-heap. But if every element of that algebra has the biunit property, which I think is the next slide probably, I think you had So if you have that property where EEA equals A for all A, right? That's called a biunit element. Right, and so a biunit pair is when instead of having EE, you have E1, E2, or EE dash something, two elements.
Yep.
And so a die heap. So a heap is a semi-heap where all elements are like E, and a die heap is a semi-heap where all elements belong to a biunit pair. So there's essentially a map that, given an element, will give you its companion. And they too make a biunit pair.
Okay.
So that's a die heap. And so the open question is: so we know there's a theorem from Wagner in the 50s, I think 50s, 60s, that they proved that heaps are equivalent to pointed heaps. So a heap with a choice of an element is equivalent to a group. It's basically the same specification.
You're just choosing the identity there.
Exactly.
Okay.
You're just choosing the identity, and then you put in the identity in the middle of the product, and that ternary product becomes binary. That's your group operation. So we define die heaps, and we show that they are non-equivalent to heaps, and they are non-empty. So we know that they, and in this talk we saw some examples. So the question is, what is the group-like analog of die heaps? If you choose a biunit, what kind of thing do you get? And we got some partial results, but nothing sufficient to find some. I mean, we actually found the correspondence. The correspondence is some kind of generalization of involutive semigroups, but it is a little bit baroque. It's what we call a switch semigroup, but it's a little bit baroque to. I don't know, maybe you like baroque aesthetics. You like it, but yeah, I can tell you more later. Yeah.
And
Thank you, Carlos, because this notion of a pair of biunits is very interesting. So it's a more general approach than the simply biunit.
Yes, and it's very natural. So I will just show you very, very quickly. So this is being published now. I mean, I'll just give you the archive because the archive is the same. So I'll post the archive on the YouTube for people watching. Oops. Oh, there it is. And I'll post it on the Zoom so you can see. So you will see I did with my colleague Bernard Rimolovic. He's now at Heriot-Watt in Edinburgh, and I was at the University of Edinburgh at the time, so we made a little collaboration about semi-heaps. You will see that the biunit pair is a supernatural concept. It is very sort of self-selected. It just cries to be defined, and yeah, it'll be great to discuss sometime in the future when you think about it, what you think, because what you find, because we basically got stuck trying to identify these die-heaps, these generalized semi-heaps that are between a heap and a semi-heap, and there seemed to be something in the middle that we were. So yeah, it's an interesting thing.
Yeah, I see. This is a very interesting paper. Yeah, Biunits, pairs, and semi-heap associated semi-groups.
Yes. Yeah. So
Thank you.
Yeah. The gist of it, just for because. So just to give you the point of it, because it will be, so if I get into this thing, the whole point is we find, let me see if I can find the equation. So die heaps are in correspondence with a kind of generalized involuted semigroup. So we know they are in correlation with some binary structure, but which generalizes groups in particular, generalizes involuted semigroups, which is a bit more general. And so this is the condition. Wait.
Which one?
This one. So switch, we call a switch. It's a name for a map. It's in a semigroup. So it's this definition basically. So it's a semigroup with a map that behaves in this way, which is a little bit baroque. Let me make it bigger. It's a bit baroque.
Now I see. Yeah, now I see.
Yeah, but you can basically see that it behaves as if it were an involution and a homeomorphism, right? But it's neither of those, right? It's neither a homomorphism nor an involution.
Yes.
You kind of assume that it works as a homeomorphism and an involution without assuming it's one. So obviously, an example of this is an actual involuted semigroup where the map is just the actual involution. So you have this relation here. Right?
Yes. Yeah.
But anyway, yes, it's a very simple paper. So I'll look forward to hearing what you think, because I think there will be some interesting follow-ups. All right, everyone. Any more questions?
Maybe just like a general approach one for all of you, maybe. Is it always possible or useful to describe these ternary structures in terms of binary ones?
Good question. Victor, you want to answer first? You heard the question?
But I didn't hear the questions.
You didn't hear the question?
Yeah, I didn't hear the question.
Okay, I'll repeat.
Can you repeat it?
Yes, I'll repeat. So Manu here was asking, is there a way to always express, right, the ternary operations in terms of binary operations?
And is it useful to do so?
And is it useful to do so?
No, I don't think so. No. We have so we have non-trivial ternary products which can be constructed by means of the binary products. So no, it's not reducible, not always reducible. Mm-hmm. So of course it's a very wide class which can be reduced to binary expressed with the help of the binary operations, but generally not.
Yes.
No.
So the products that Victor was showing today, which were the fish and this twisted fish, they already tell you that that's not quite the case, because even though you can express them as A times B transpose times C, that's not just a binary operation. It's a binary and a unary operation. You have the multiplication and the transpose, right? So already in this very simple example, you see that the ternary product, I think the fish is the easiest of all the ternary products in a sense, because it's the closest to the familiar territory. Already in this case, we see that it's not that the ternary decomposes into. And I think there is some theorem in what is called the N group or P group or P-adic group, sometimes literature, about general P groups, so P area associative operations, there is some result there that tells you that when you introduce a unit element, you automatically collapse into a composition of binary operations. So essentially, the moment you have an identity element, you can put it in between the ternary product and you get a binary product.
Right.
So when the operation is associative, and there's some condition I can't remember, you can always decompose any NRE operation into a lower arity operation. But this is only when you have associativity, so strong associativity, meaning that you can associate all brackets, and you introduce identity elements in the usual sense, in the traditional sense. So in that way, you can reduce, but by the way, none of the products that Viktor or Richard have shown today about with this hypermatrices, none of them satisfy associativity in the usual sense. This is something that I think we didn't mention that much, but because we are very used to this fact, but none of these products are nowhere near associative. I mean, the closest is this fish thing, this is semi-heap, which is kind of like a twist of associativity, but that's the closest thing we have. Everything else is unknown, what kind of properties they satisfy. Like this Jacobi, we don't know. Associativity, we don't know. I mean, we know it's not associativity, but we don't know if there's something like associativity, but higher order. And yeah, it's a mystery still.
Yeah, Carlos, I would like to mention a very wide, a very large class of so-called Ternary Lie algebras, which were introduced by Filippov. And
Yes.
so in these algebras, we have an Ternary operation which constructed in this way that you cannot reduce it to a -1 or ternary to binary because they use some kind of an approach of Jacobian. You have an element and the derivation in algebra, and then you write in a Jacobian. This cannot be reduced to a binary. No, it's a very wide class of.
Correct. That's an excellent example, Victor. Actually, just before your talk, we were talking about this Filippov algebras. The name Filippov is written on the blackboard here, actually. So, actually, that's a very good example. And even though Filippov algebras might sound a little bit esoteric for those of you unfamiliar, you actually already know Filippov algebras, what people call the affine Filippov algebras. So you know how you have how you can define the cross product in 3 dimensions with the determinant formula. You put exactly and so on. So you can imagine that formula actually doesn't care about dimension. So if you go 1 dimension lower, you have ij and then just 2 entries, which will be 1 vector. That's the complex structure, right? It's like the complex rotation by 90 degrees. But if you go 1 dimension higher, you go to 4 dimensions. Now you have whatever A1, A2, A3, A4, and then to complete the square, you would need 3 rows, right?
Yes.
So that's that ternary product in 4 dimensions, and that product satisfies exactly that formula, the Filippov condition, the Jacobi identity condition, and that is absolutely not reducible to any. It's like saying the cross product is reducible to something that is composition of unitaries or something like that. It's not at all. So yeah, and each dimension has at the top at the sort of top -1 dimension, you have at n dimensions you have an n-1 array Filippov algebra. And so in n equals 3, that's the cross product, the familiar cross product. In n equals 4 is this ternary one that we studied a little bit, but in all dimensions you have this. And these are all inequivalent to anything known. These are their own algebras. They are their own thing. Yeah.
Yeah, that's a good example of this extension of the cross product to higher dimensions.
Yes, it's a very nice example. I like it. Yes. And I complain with because many physicists and many mathematicians say there's only a cross product in 3 dimensions and 7 dimensions. No. There are cross products in all dimensions. You call them differently. Yes, it's funny.
Is there a sense to thinking about heaps with just left or just right Biunits?
I will repeat the question just for you to hear, Victor. So the question was: is there a sense in which it makes sense to think of heaps with either, semi-heaps with either left Biunits or right Biunits? And do you have any examples maybe of what these things mean or represent? I personally don't.
No, I don't. No, I don't have these examples. No.
No. This.
But
Yeah. And yeah, actually, in the I think it was in the paper that you mentioned, Victor, about the heaps of fish paper. You see this. I will share very quickly because it's a way to understand semi-heaps, or actually heaps, is that any if you're in a groupoid. Are you familiar with groupoids at all? Okay, so groupoids are this relaxed version of a group. So basically, when you have group-like behavior, but you don't impose that all elements must multiply all elements. Okay. Are you familiar with categories a little bit? Yeah, so a groupoid is a category where all morphisms are invertible.
Okay.
That's it.
The question size.
So basically, so Victor, this is where we quoted your paper in our so we can quote each other. And so there's this section about heaps. If you're curious, I think this is a good reference to get a sense of heaps.
Yeah.
And my summary of heaps conceptually was this diagram. So basically, when you have a groupoid, which is a category where all arrows are invertible, if you take an object and you look at all the arrows that go from the object to itself, because you're claiming that all arrows are invertible, the set of all arrows that go from an object to itself is a group. And that's what people call the isotropic group or the vertex group or something like that of a groupoid. Okay. And so this is very well known in the literature. Everyone thinks of groupoids as essentially connected groups by a network of, so that is not necessarily on a single vertex, right? It has more than one center. So that's a good way to think of groupoids. A groupoid is kind of like you take the identity and you kind of blow it up to several identities. And then around each identity, you have a little group. So the observation that I did in this paper is that if you, instead of considering the arrows from an object to itself, you consider the arrows from an object to an object, different objects, the structure that you get in the space of arrows is that of a heap, in fact. So in the same way that you get the structure of the algebraic structure of a group in the arrow set of an object, you get the structure of a heap in the arrow set between two distinct objects. So obviously, if you put the same object twice, you get the heap that will give you the group that is the thing. But if you don't, then you actually just have a heap in general that will give you that operation. And the interesting thing is that obviously there is no choice of, so here the left and right Biunits are given by identities on one object or the other. So they are actually separate.
Right.
So I'm not giving you much of an example, but I'm giving you sort of what I think is the natural space for these things to happen. And if you're ever, maybe you've heard of dagger categories before. So dagger categories are actually the natural environment of semi-heaps, because the most minimal example of a semi-heap is this construction, where you have two objects, A, B, and then you take three morphisms, F, G, H, going in the same direction. And then you reverse one of them with a dagger, and then you can compose in a zigzag diagram, right? So you end up in B from A to B. So that composition satisfies precisely the semi-heap axiom by the axioms of categories and daggers, right? Cool. So if you ever want to think of semi-heaps in a concrete sense, you can always think a dagger category. Every morphism group, every morphism set of a dagger category is a semi-heap. Canonically. So yeah, that's another way to say it. Anyway, sorry, that was just the context for the semi-heaps.
Let's thank Victor.
Yes.
For the brilliant talk. Thank you so much.
Thank you so much, Victor.
Thank you. Thank you. And please, if you want to put any papers also in YouTube, maybe from Victor, it would be great to have them.
Yes, send us the papers, and
you can maybe include them.
And maybe the slides as well, if you want. If you can send us the slides, people can have access to them. If you're happy to.
Okay, I will send this. Yes. Okay.
Perfect, Victor. Thank you very much.
Thank you.
Yeah.
Yes.
Bye-bye.
Bye, and thank you, everyone. We'll see you tomorrow at the same time.
Bye, Olga.
Goodbye, James.
Bye. Bye.
Bye-bye.